Next, we'll cover decoders and encoders. We know an n-bit binary code is capable of representing up to 2 to the power n distinct elements of codes. Suppose we will provide n inputs from which we'll get m number of outputs in such a way that each valid input code word produces a unique output code. This will follow this condition where n is the number of inputs. For this case, n will be less than or equals to m. That means number of outputs will be greater than number of inputs or equals to number of inputs. And by using n inputs, we can have maximum 2 to the power n number of distinct output. That's why this output cannot be greater than this 2 to the power n numbers. We can say this m output will be definitely less than or equals to 2 to the power n. When we construct an input-output relationship in this way that is named as n into m decoder, sometimes it is called n to m line decoder as well. From this relationship, we can assume that the decoder may have unused bit combinations on its input for which no corresponding m bit code appears at the output. The idea will be more clear when I'll show you some examples. Let us start with 2 to 4 line decoder designing. 2 to 4 line decoder. Sometimes it is written as 2 into 4 decoder. That means we will have 2 inputs and 4 outputs. In 2 to 4 line decoders, we will have only 2 inputs and there will be 4 distinct outputs. Suppose the inputs are I0, I1 and the outputs are D0, D1, D2, D3. This is 2 into 4. Using 2-bit numbers, we can have 4 combinations. They are 0, 0, 0, 1, 1, 0, 1, 1. That is why output can have maximum 4 numbers of output. Now let me explain the function of this 2 into 4 decoder. Whenever the inputs will have combinations of 0, 0, that means I0 equals to 0, I1 equals to 0, only D0 output will be activated. That means D0 output will be high, others will be low. For 0, 1, D1 will be high, others will be low. For 1, 0, D2 will be high, others will be low. For 1, 1, D3 will be high, others will be low. So this is the basic operation of 2 into 4 decoder. If we draw the truth table, we have 2 inputs and 4 outputs. I1, I0. Here the outputs are D0, D1, D2 and finally D3. The input combinations are 0, 0, 0, 1, 1, 0, 1, 1. When 0, 0 input is given, D0 will be 1, others will be 0. When 0, 1 input is given, D1 will be 1, others will be 0. When 1, 0 input is given, D2 will be 1, others will be 0. For 1, 1 input, D3 output will be 1. So each high output will represent the one distinct combination of input set. Let us draw the logic diagram for this. We have 2 inputs, I1, I0. This line will represent I1 input, this line will represent I0 input. And these 2 lines will represent I0 prime and I1 prime. For D0 to be 1, both the inputs of I0 and I1 will be 0. For that case, the function output can be implemented by taking the inputs from I0 prime and I1 prime. They will be ANDed and we'll get D0 output. Here it is to be mentioned that all these outputs are the representation of the min terms of the input. Here I1 prime, I0 prime. Here this will be 1 for I1 prime, I0. Here this will be prime for I1, I0 prime. That means 1, 0. And this will be 1 for I1, I0. And from our previous lecture, we know this is the min-term representation of the input combinations. Now for D1, we need to AND the I1 prime and I0. So I1 prime can be taken from here and I0 will be taken from, they will be ANDed, and the output will represent D1 output. So D1 will be 1 only for 0, 1 input. For other inputs, D1 will be 0. We can see from here. Next, D2 will be I1 ANDed with I0 prime. So we can take I1 that will be ANDed with I0 prime. This will give us D2. Finally, I1 and I0 will give us D3. So I1, I0, they will be ANDed, and that will return us D3. This is the logic diagram of a 2 into 4 decoder. Inside this block, we have this circuit. This is the block diagram of a 3 into 8-bit decoder. We have 3 inputs and we have 2 to the power 3, that means 8 outputs. These are the min-term representations of each output case. Like the previous one, each output will represent one distinct set of inputs. This is the truth table for this 3 into 8 decoder. We have A, B, C, 3 inputs. Using 3-bit inputs, we can have 8 combinations, and this is the output for the 3 into 8 decoder. Let us start drawing the logic diagram. We have 3 inputs, A, B, and C. These 3 lines will represent A, B, C. This will represent A prime. This line will represent B prime, and this line will represent C prime. First, this D0 output will have A prime, B prime, C prime. So we can take A prime, B prime, C prime. They will be ANDed, and the output will be represented by D0, which actually means A prime, B prime, C prime. Similarly, we can draw the logic diagrams for other conditions. Let us keep drawing. We need total 8 AND gates for D0 output, D1 output, up to D7. A prime, B, C prime. Next, A prime, B, C, A prime, A, B prime, C prime. So finally, this is the logic diagram for 3 into 8-bit decoder. Next, we will see decoders with enable inputs. What is the enable input? See an example using 3 into 8 decoders. This is the block diagram of 3 into 8 decoder, and we know how to construct this circuit. In a decoder with enabling options, there will be another input which represents enable inputs. It is represented by En. What is the function of this enable input? If enable equals to 1, that means En equals to 1, then this 3 into 8 decoder will function properly. For example, if enable equals to 1, then if A, B, C equals to 0, 0, 0, then D0 will be 1, others will be 0. If A, B, C equals to 1, 1, 1, then D7 will be 1, others will be 0. But if enable equals to 0, whatever the inputs we give, all the time outputs will be 0. That means it is disabling the decoder circuit. So if I draw the truth table, then we will get a better picture. We have 3 inputs A, B, C, and outputs are D0, D1, D2, D5, D6, and finally D. And we have one more input, that is enable. Now if enable equals to 0, whatever the input we give in A, B, C, the output will be always 0. Now if enable equals to 1, then if we give 0 0 0 in ABC, then D0 will be 1, others will be 0. In this way, this decoder will operate normally for enable equals to 1. So this is the truth table for this 3 into 8 decoder with enable input. Now let us draw the logic diagram for this. We'll be using the previously constructed 3 into 8 decoder logic diagram for this purpose. This is the logic diagram for 3 into 8 decoder without the enable pin. Now the function of the enable pin is to enable the decoder circuit, for which we'll get the output properly. If enable equals to 1, then this 3 into 8 decoder will operate properly. If enable equals to 0, whatever input we give, all the outputs will give us 0. In order to construct that, what we need to do, we need to provide one extra input to all the AND gates, which will be connected with enable pin. So another input will pass through this line to this AND gate, and these are connected. Now if we see the operation, if enable equals to 0, then one of the inputs of the all AND gates will be 0. In that case, whatever input I give to A, B, C, all the time the output will get 0, because one of the inputs of this AND gates is 0 due to enable equals to 0. But if enable equals to 1, that means this line will be providing high input to this AND gate. Then the output will be decided by the input combinations of A, B, C. If A, B, C equals to 0 0 0, then D0 will be 1, others will be 0. If A, B, C equals to 1 1 1, then D7 will be 1, others will be 0. In this way it will work as per the condition given in this truth table. So this is very easily implemented. This is 3 into 8 decoder with enable pin. Now if you are asked to design a 4 into 16-bit decoder with enable pin, I hope you'll be able to design that. Next we'll see the construction of 4 into 16 decoder using two 3 into 8 decoders. This is the block diagram of 3 into 8 decoder, and we know the internal circuit diagram of this type of decoder, which was designed earlier. We can construct 4 into 16-bit decoder using the conventional method that was shown earlier. But if it is asked to design a 4 into 16-bit decoder using two 3 into 8 decoder, we may follow this procedure. Here we'll need two 3 into 8 decoders. So let's copy this. We have two 3 into 8 decoder. In 4 into 16-bit decoder, there will be 4 inputs and 16 outputs. We can see we have 16 output lines here. We will be using these outputs for 4 into 16-bit decoder. Here we have 3 inputs. This is LSB. I0 is LSB. So what we are going to do, we'll short this I0, I1, finally I2. They will be shorted. Now if we provide 0 0 0, then I0 will be 0, I1 will be 0, I2 will be 0. So the first output D0 will be activated for the first decoder, and the first output of the second decoder will also be activated. So what we can do, we can use this enable pin as our MSB. So this can be used as MSB. In that case, this can be denoted by I3. So we have I0, I1, I2, I3. This I3 can be sent through a NOT gate, and enable pin will be connected directly with the enable pin of the second decoder. So if we connect it, it will have this type of formation. Here these two are connected. Now if we have I3, I2, I1, I0, if all these values are having 0, 0, 0, 0, what will happen? When I3 equals to 0, that means we are providing enable equals to 0, and this is directly connected with the second decoder. So this decoder will be deactivated and this 0 will be inverted here. That means we'll get 1 here. That means the enable input of this decoder is getting 1 here. So what will happen whenever we are providing 0, 0, 0 for I0, I1 and I2, the first output D0 will be activated, others will be deactivated. Remember here we are getting 0, 0, 0 here as well in the second decoder, but as this enable pin is 0, that means this is disabled, so all the outputs will be 0 here. So we can say for 0, 0, 0, 0 4-bit inputs, we are getting only D0 output as high, others will be low. Let's name this D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. Now if we provide 0, 0, 0, 1, what will happen? As I3 equals to 0, I3 equals to 0, so this is still deactivated. So we are giving 0, 0, 1 to both the inputs, but as it is deactivated, so all the outputs will be 0. Only D1 will be activated. That means D1 will be high, others will be low. In this way, if we keep going, whenever I3 equals to 1, and again we are providing 0, 0, 0, what will happen? I3 equals to 1 means this second decoder is activated and 1 will be inverted here and the first decoder will be deactivated. This is disabled. So even though it's getting I0 equals to 0, I1 equals to 0 and I2 equals to 0, but as this decoder is deactivated, all the outputs here will be 0 here. As we are having 0, 0, 0 here, the first output of the second decoder, that is D8, will be high, others will be low. In this way, we can get the outputs for 1, 1, 1, 1 case, and for that D15 will be activated, others will be deactivated. In this way, we can construct a 4 into 16-bit decoder using 2, 3 into 8-bit decoder. Next, we will see decoder-based combinational circuits. That means we will implement functions using decoders. We know for n input variables, a decoder provides 2 to the power n number of minterms. Since any Boolean function can be expressed as a sum of minterms, one can use a decoder to generate the minterms and combine them with an external OR gate to form a sum of minterm implementation. In this way, any combinational circuit with n inputs and m outputs can be implemented with n2 to the power n line decoder and m number of OR gates. So the procedure is very simple. First of all, we need to express the function in sum of minterms form, then check the number of inputs, then use the decoder which has that number of inputs. Let me show you an example. For the full adder that we designed earlier, the sum expression was C in B A was having this formation, summation of minterms 1, 2, 4, 7, and the carry out that we designed, that was having C in B A, sum of minterms, that was having 3, 5, 6, 7. This is the function for a full adder circuit that has a function block like this, and we designed the internal logic diagram earlier. Now we'll design the same circuit using decoder. So how many inputs are there? We can see from here we have 3 inputs, C in, B and A. And how many outputs are there? There are 2 outputs. One is sum, another is C out. In order to implement this circuit, we need to use 3 into 8-bit decoder. Here this is the block diagram of a 3 into 8-bit decoder, where we have C in, A, B, 3 inputs and 8 outputs. Now, if we want to implement this sum function and cout function using this 3 into 8-bit decoder, we can say this can be represented by as we have in sum of midterms form, we have 1, that means 0, 0, 1, which can be represented by C in prime B prime A, plus 2 means 0, 1, 0, C in prime B A prime, plus 4 means 1, 0, 0, C in A prime B prime, plus 7 means 1, 1, 1, C in A B. Again 3 means 0, 1, 1, C in prime B A, plus 5 means 1, 0, 1, C in B prime A, plus C in B A prime, plus C in. We know D0 output is a representation of minterms C in prime A prime B prime. Here C in is the MSB and A is LSB, so it's better right in this fashion, C in B A. So D0 is the representation of C in prime B prime A prime, and D1 is the representation of C in prime B prime A, which is here. So this output or this output or this output or this output. So we can draw an OR gate for some output. This OR gate will be fed by 1, 2, 4, 7. So we can take output from here 1, another from here 2, another from here 4, finally, and this output will give us the sum output. Next, for C out, we need to draw another OR gate. This OR gate will be fed by 3, 5, 6, 7. We have 3, then 5, 6, finally 7. This will give us C out. In this way, we can implement any function using decoders by expressing the function in sum of minterms form. Encoders. An encoder is a combinational logic circuit that essentially performs a reverse decoder function. In decoders, we had n inputs and 2 to the power n number of outputs. For each distinct combination of inputs, we had one of the outputs activated. Now for an encoder, it accepts an active level on one of its input representing a digit and converts it to a coded output. Let me show you an example using 8 into 3-bit encoder. 8 into 3-bit encoder means we have 8 inputs and 3 outputs. This is the block diagram of an 8 into 3-bit encoder. We have 8 inputs and 3 outputs. In 8 inputs starting from I0 to I7, the 3 outputs are X, Y, Z, where X represents the MSB and Z represents the LSB. Now let me describe the function of this encoder. Whenever I0 will be 1 and others will be 0, that will produce a unique code. For example, for I0 equals to 1, it will produce 0, 0, 0. For I1 equals to 1, while the other inputs are 0, it will produce 0, 0, 1. For I2 equals to 1, while the others are 0, it will produce 0, 1, 0. In this way, whenever I7 equals to 1, it will produce 1, 1, 1. This is the truth table for the encoder that I described. Whenever I0 equals to 1 and others are 0, then it will produce unique output code that is 0, 0, 0. I1 equals to 1 while the other inputs are 0, it will produce a unique output code that is 0, 0, 1. In this way, we'll have 8 combinations for 8 input cases. Now the resulting output equations for the each output variables, we can say x will be 1 when I4 equals to 1 or I5 or I6 or I7. Then y equals to 1 for I2 or I3 or I6 or I7. Finally, Z will be 1 for I1 or I3, I5. Now, if we draw the logic diagram, we record the inputs I1, I2, I3, I4, I5, I6, I7. For 3 variables, we need 3 OR gates. This is the first OR gate, the second OR gate, and this is the third OR. First OR gate will be fed by I4, I5, I6, I7. I4, I5, I6. This will give us X. Next, Y is the combination of I2 or I3 or I6 or I7. So let us start from I2 or I3, I6 can be taken from here, or I7. This will give us Y. Next, Z, I1, and I3, I5, I7, I7. This will give us Z. So this is the logic diagram of 8 into 3-bit encoder. Next, we'll be discussing about a special type of encoder, that is priority encoder. In general, a priority encoder is a combinational circuit that implements a priority functions. The operation of priority encoder is such that if 2 or more inputs are equal to 1 at the same time, the input having the highest priority dominates. Let me show you using this example. Suppose we have a 4 into 2 priority encoders. In input side we have 4 inputs, and in output side we have 2 outputs. For 4 inputs we can have 4 combinations of outputs: 0 0, 0 1, 1 0, 1 1. Now if we provide this input as the lowest priority and I3 is having the highest priority, and the priority order moves in this way. That means I1 is having higher priority than the I0, I2 is having the higher priority than the I0 and I1, and I3 is having the highest priority. What does that mean? When I0 equals to 1, this will produce 0 0. No problem, we know from our previous topic. Now, if I0 equals to 1 and I1 also equals to 1, both are 1, then what will be the output? In this case, as I1 is having higher priority than I0, so the corresponding code for I1 that will be produced here, that is 0 1. In this way, when I3 equals to 1, I0 equals to 1, and I1 equals to 1, and I2 equals to 0, even though these two inputs are 1, but as the I3 is having the highest priority, so eventually it will produce 1. So in this way it works. Here I want to mention one thing, that when I0 equals to 1 and others are 0, it will produce 0 0. Again, when we are not providing any input, it may produce 0 0. So for the both cases, when we are not giving any input, we are getting 0 0, and when I0 equals to 1 and others are 0, we are getting 0 0. Here, when I1 equals to 1 and others are 0, and that is producing 0 0, that is the valid output. When all the inputs are 0 and it's producing 0 0, that is invalid output. That is why, in order to show the output whether it is valid or invalid, a new output is defined, that is V. If V equals to 0, then the output that is appearing here is invalid. If V equals to 1, which represents that the output that is appearing here is valid. So let us construct the logic diagram for this. First of all, we'll construct the truth table, which will give you a clear picture of this priority encoder. We have inputs I0, I1, I2, and finally I3, and the outputs are A1, A0, and this is V. Now when all the inputs are 0, 0, 0, 0, then the outputs A0, A1, we don't care. The V output should be 0 in order to show that the output that is appearing here is invalid. Now when we have I0 equals to 1, I1 0, I2 0, I3 0, then it must produce 0, 0 and the output will be valid. That's why V equals to 1. When I1 equals to 1, I don't care about whether I0 equals to 0 or 1, as I1 is having higher priority than I0. So we'll place a don't care condition here and we'll say it will produce 0, 1. And this is valid out. Again, when I2 equals to 1, as I2 is having higher priority than I0 and I1, so we do not care about these inputs. So it will produce 1, 0, and this is valid out. When I3 is having one value which has the highest priority, then we do not care about other inputs. It will produce 1, 1, and this is valid out. Now let us construct the function for each output variable. Take this here. As we have 4 inputs and 3 outputs, we need to use kernel map. For A1, A0, we'll be using 2 kernel map. For the output V, it is obvious. It is I0 or I1 or I2 or I3. Here I0, I1, I2, I3, having I0, I3. This kernel map is for A1 and this is for A0. For A1, A1 equals to 1 when I2 equals to 1 and I3 equals to 0, and I0, I1 don't care conditions. So for all the combinations of I0 and I1, this is true. We have I2 equals to 1 and I3 equals to 0, this column, and we can write 1 for all the combinations of I0, I1. Similarly, for this one, I3 equals to 1, we have I3 equals to 1 in this 2 column, and for all other combinations, it is true. So we can write once here, boxes, and we have one don't care condition for 0, 0, 0, 0. Don't care condition here. Now we can take this box and another box, and A1 can be written as I2 plus. Next, for A0, we are having A0 equals to 1 for this case when I1 equals to 1 and I0 is having don't care condition. I1 equals to 1 is in this line and I0 is having don't care condition. So all the combinations for I0, it is true. We can place 1, 1 here. Another condition is that we have 1 here. So we know this. We need to place 1s here. Now we can take this box and this box. So A0 can be written as I3 plus I1, I2 prime. And V is having this expression I0 plus I1 plus I2 plus I3. Now let us draw the logic diagram. Logic diagram. We have 4 inputs I0, I1, I2, I3. First output will be A1, which is equal to I2 or I3, I2 or I3. The output will be A1. Next, the output A0 can be written as I3 or I1 ANDed with I2 prime, and one not get here. I2 prime will pass through this and another input will come from I1. Output of this AND gate will go there and this will give us A0. Finally, for V, it will be I0 or I1, or this is I2, or I3. This will give us V. This is the logic diagram of the priority encoder that is defined here.